As the sun sets on a tranquil ocean, the immensity of a Nimitz-class aircraft carrier fills the frame. Towed smoothly by tugboats, the floating fortress is a behemoth, measuring over 1,000 feet long and displacing approximately 100,000 tons. This magnificent ship, powered by nuclear reactors, can carry a full complement of 90 aircraft, enormous quantities of fuel, munitions, and supplies. Yet, gliding over waves, it appears almost serene. How is it that a structure with this mass remains afloat, supported by nothing and defying the laws of gravity? This raises an intriguing question: why do aircraft carriers float with a city's worth of steel resting confidently on their deck? Amidst the complexity of water, gravity, and structure, the secret lies in the principles of buoyancy and metacentric height, mechanisms that govern not just the carrier's flotation, but its stability in the tempestuous seas. To unravel this mystery, we must first comprehend buoyancy, the force that supports an object submerged in fluid. This principle, long established by Archimedes, asserts that any object submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces. Picture a person floating in a pool. They drift effortlessly, as their body pushes water away, experiencing an upward force that keeps them buoyant. In terms of our aircraft carrier, it displaces a volume of seawater equal to its weight. The Nimitz-class carrier displaces about 100,000 tons of water, generating a significant buoyant force. To visualize this, imagine an enormous block of ice breaking the surface of a lake. While its mass might seem daunting, it floats effortlessly, supported by the very liquid it displaces. However, buoyancy alone is not enough to maintain stability. A floating vessel's metacentric height, or GM, plays a critical role in preventing capsizing. This measurement refers to the distance between the center of gravity of the ship and its metacenter, the point around which the ship pivots when tilted. The greater the GM, the more stable the vessel. For the Nimitz-class aircraft carrier, engineers aim for a GM that offers an optimum balance between stability and performance. This vessel boasts a metacentric height of roughly 21 feet. With such a height, the carrier ensures that the center of gravity remains low enough to counterbalance any forces causing it to tilt. As heavy payloads are loaded, careful design considerations are built in to maintain this crucial relationship, ensuring the center of gravity remains suitably positioned. To fully grasp the dynamics of stability, consider the example of a toy top. When it's spinning, the top remains upright, drawn into a center of rotational stability. If it begins to lean, gravity pulls it further off balance, but its rotation and the force from the base work to keep it aloft, at least for a while. In the case of an aircraft carrier, the engineers have effectively engineered a similar dynamic. The heavy metal of the ship's hull is structured around a stable center of gravity while buoyancy works to keep it afloat, crafting a balance that is remarkable in its precision. But how do engineers maintain and manipulate this delicate balance? The answer lies in sophisticated ballast management systems, designed to adjust the ship's weight distribution in real time. These systems employ a series of void compartments located throughout the hull which can be filled or emptied with seawater at will. Consider this: as the carrier prepares to accept a load of aircraft, bombs, and fuel, the internal compartments can be flooded, allowing the ship to lower into the water, adjusting the center of gravity and enhancing stability. As the carrier takes on significant weight, the underwater hull geometry remains critical. The hull is designed with a deep draft and a wide beam, characteristics that extend the vessel's stability. The combination of these factors provides a buffer against capsizing, even in tumultuous seas. This integrated design allows a previously absurd thought to become reality: a ship carrying tens of thousands of tons of steel can traverse ocean swells and crosswinds, all without compromising its structural integrity. However, with such powerful systems comes extraordinary responsibility. Consider the case of the USS Theodore Roosevelt, a Nimitz-class carrier that made operational headlines in 2020. This aircraft carrier faced a challenging situation when an outbreak of illness on board complicated its loading and unloading processes. The alteration in ballast loading could impact the center of gravity and stability, ultimately risking the integrity of a ship that is a floating city in itself. This incident highlights the importance of precise engineering and management on board such vessels. But what happens when engineers receive unexpected cargo, such as an unforeseen shift in fuel load or changes in flight operations? A common misconception is that aircraft carriers can simply adapt to any situation without consequence. In truth, the balancing act is far more delicate. The practice of weight distribution aboard marine vessels is a critical task, and when not managed properly, it could have dire consequences. Now, a brief moment for reflection. Which of these machines would you least want to be standing next to? An aircraft carrier, with its tremendous weight and military power, or a massive cargo ship, transporting goods across oceans? Tell us your thoughts below. Continuing with our exploration of false assumptions, it's common for many to believe that increasing the weight of a ship would necessitate increasing its buoyancy. However, the opposite often proves true. Engineers prefer to lower the ship's whole design, maintaining buoyancy with a precise, optimized compromise of weight distribution. This keeps the ship from leaning excessively, only succeeding through intelligent design choices that consider all aspects of operations. The twist in our exploration reveals that the geometry of the hull is past simply aesthetic, its efficiency is vital for performance at sea. The significant volume the hull displaces is achieved not just through its size but through defined curves and structural components that work cohesively to channel water around the ship, minimizing drag and enhancing sea-staying ability. Engineers meticulously calculate how each bolt and panel interacts with water flows, ensuring that as the ship travels at speeds of 35 miles per hour, its design is efficient, optimized, and most importantly, stable. In an awe-inspiring culmination, every component working together creates a powerful illusion. A massively heavy aircraft carrier can move, turn, and operate in harmony with turbulent seas, all with a buoyancy and stability that belies its sheer scale. This floating city, constructed with precision engineering, is a testament to human innovation and the mastery of natural forces. To further encapsulate our lesson, remember this: the secret of how aircraft carriers defy gravity rests not solely on their displacement, but on the thoughtful orchestration of buoyancy, metacentric height, ballast management, and meticulously designed hull shapes. Together, these elements ensure that a ship with the weight of a small city can effortlessly glide through the ocean, offering the world an unparalleled display of engineering marvel. The invisible threads of engineering are woven deeply into the fabric of our daily lives. It is through understanding these complexities that we come to appreciate the ingenuity behind the machines we take for granted. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you. To further appreciate the engineering prowess of aircraft carriers, let us delve deeper into the specifics of hull design and stability mechanisms. The Nimitz-class aircraft carriers are not merely constructions of steel, they are marvels of hydrodynamic engineering. The shape of the hull is not just a design choice, it is meticulously crafted to optimize various performance metrics, including fuel efficiency, top speed, and, most importantly, stability. The most striking feature of the Nimitz-class hull is its robust form, with a length of over 1,000 feet and a beam of roughly 133 feet. This wide beam contributes significantly to the vessel's stability. A wider hull increases the waterplane area, providing more surface area to counteract forces that would lean the ship to one side. When the vessel is subjected to lateral forces from heavy seas or wind, the buoyant force acts more effectively, resisting capsizing. Imagine a person attempting to balance on a tightrope versus standing on a wide beam. The latter offers a greater base of support, making it easier to maintain balance. In addition to these physical dimensions, consider the underwater shape of the hull. The design reflects a fundamental understanding of fluid dynamics. The Nimitz-class features a deep draft of roughly 35 feet. This depth allows the keel of the ship to remain submerged, minimizing the effects of surface swells on the overall stability. The interactions of the hull with water are intricate, and better understanding these mechanisms helps clarify just how effectively the Nimitz-class can manage its grand size in complex conditions. As the Nimitz sails, it is not simply riding the waves, it is actively engaging with them. Engineers apply the principles of hydrodynamics, how fluids move, to design the curves and angles of the hull. Each angle affects how water is channeled around the vessel, directly influencing drag and stabilizing forces. The hull shape, often compared to a giant wedge, increases efficiency while cutting through water with minimal resistance. To visualize this principle, think about how a well-designed boat slices through waves compared to a boxy hull that might slam against the water, creating turbulent swells. A critical example of how these principles are applied can be found in the story of USS Ronald Reagan, another Nimitz-class carrier, which underwent a midlife refurbishment that included updates to its hull design. Engineers took the opportunity to refine the underwater structure, enhancing aspects that can improve hydrodynamic performance anywhere from 5 to 10%. Such changes, seemingly minor, can have substantial effects on fuel efficiency and overall stability, particularly in challenging weather conditions. Now, let us consider the ballast management system in more detail. While the basic principle of adjusting weight distribution was introduced earlier, the complexity of this system is remarkable. The system consists of multiple tanks located throughout the hull, capable of being filled with seawater or emptied as needed. Engineers have designed these tanks to be strategically positioned to ensure that weight is distributed evenly across the vessel. In the dynamic environment of the open ocean, being able to adjust the ballast in real time contributes significantly to maintaining not only stability but also operational readiness. Take a moment to envision a large container of water. If you were to tilt it, it would spill out. In the case of an aircraft carrier, the water inside those ballast tanks must be managed continuously to ensure that the ship responds to external forces appropriately. When aircraft are ditched into the hangar or fuel levels change significantly, ballast tanks can be adjusted to counterbalance these shifts instantly, maintaining that critical metacentric height we discussed earlier. Consider the historical instance of the USS John C. Stennis, a Nimitz-class carrier, during a major operation involving the transportation of aircraft and supplies. Upon receiving unexpected heavy cargo, the crew had to rapidly adjust their ballast system. With the swift addition of seawater to specific tanks, they were able to lower the center of gravity to counteract the extra weight and maintain the carrier's stability amidst heavy seas. The engineer's expertise shines further through the use of dynamic positioning systems, which can help control the ship's motion in complex seas. This technology uses a combination of propeller thrust and hydraulic rudders. By adjusting how thrust is distributed among various propulsion units, the carrier can effectively manage not just its trajectory but also stabilize against unwanted movements caused by waves or wind. This brings us to another crucial thread in the carrier's design, its propulsion system. A Nimitz-class aircraft carrier is powered by 2 nuclear reactors, generating roughly 260,000 shaft horsepower. This immense power is not simply for forward thrust, it is also integral in maneuvering the ship in tight quarters or in stormy conditions. With this level of power, the carrier can operate in various scenarios, from launching aircraft under tumultuous weather to zigzagging through tight formations with other vessels. In moments when speed is required, such as during launch operations, the carrier can go from stationary to over 35 miles per hour, allowing it to adjust its positioning rapidly against the backdrop of changing environmental conditions. While the performance might seem straightforward, the balance of mass, momentum, and hydrodynamics is actively managed in real time by the crew, embodying a host of engineering principles. While we consider a carrier like the USS Dwight D. Eisenhower, which supports operations for extended periods, resource management comes to the forefront. The weight of fuel and supplies needs to be constantly calculated and reassessed in real time. If the operational need shifts and requires offloading fuel, an exact weight reduction could upend a precarious balance that maintains the ship's stability. Compensatory measures must be taken fast, deploying ballast water or making adjustments to aircraft and cargo placements. Now, let's return to the concept of the metacentric. Engineers understand that capturing the right relationship between buoyancy and metacentric height is what allows carriers not merely to float but to do so without fear of capsizing in harsh conditions. One major advantage of the Nimitz-class design is the use of lower-slung internal structures that keep the center of gravity low. By leveraging this knowledge, engineers can enhance the resilience of these vessels, allowing them to operate in diverse maritime conditions. An interesting misconception to address is the belief that aircraft carriers have to remain upright at all times. Engineering fatigue can mislead some to think that as long as there is buoyancy, survival is assured. In reality, aircraft carriers can tolerate significant rolling to a limit known as the angle of vanishing stability. This is a critical engineering threshold. If the rolling exceeds a certain degree, balance can be lost, leading to potential capsizing. Thus, Nimitz carriers are engineered to roll safely within a defined limit without risking the stability of their aircraft operations. In our understanding of the ecosystem surrounding these naval giants, we learn that the engineering feats do not belong solely to the carriers themselves. Instead, they extend to the supporting crew, whose training ensures the ship operates smoothly, from the highest ranks of naval command to the enlisted sailors who work tirelessly to ensure all systems maintain their integrity. Each crew member is trained to understand the principles of stability, buoyancy, and weight management, creating a human aspect that complements the robust technological foundation. In conclusion, the engineering behind aircraft carriers not only captivates but also inspires. Strength, stability, and advanced technologies intertwine to create vessels capable of defying the ocean's vast challenges. Understanding the nuances of buoyancy, metacentric height, ballast management, and hull dynamics provides crucial insight into how these floating cities are more than just steel giants, they are a symphony of physics and human ingenuity. As you walk away from this deep dive exploration into the science of floating, remember that the unseen integration of design, engineering, and execution creates a balance that allows aircraft carriers to sail confidently across the unyielding sea. The world of engineering teaches us that amidst the colossal, it is often the meticulous details that hold the greatest power. The bigger the machine,